have the pleasure of delivering our work titled Adversarial Examples for Proof of Learning. What motivated our work was two major challenges in machine learning. The first is a challenge of machine learning intellectual property resolution, which asks the question, how can a model owner prove that they produced a model? This is an open and difficult challenge in ML that arises due to the popular model extraction attack. Given some publicly hosted model, an adversary employing this attack can reverse engineering a model by querying it. Here, an arbitrator may be needed to facilitate ownership resolution. The second challenge surrounds Byzantine workers in distributed and collaborative learning setups, which are of growing popularity in the machine learning community. Here we see a central server with distributed workers across the bottom. We pondered what happened when Byzantine workers deviated from the designated collaborative protocol and then asked ourselves, is there a way to verify computations made by distributed workers? There are really three related works that address these questions of ownership resolution and Byzantine workers in collaborative learning. These are watermarking defenses and fingerprinting for the former, or verifiable computations for the latter. However, both watermarking and fingerprinting lead to unfavorable trade-offs between their success and the model utility, meaning that it can be difficult to employ these solutions while attaining similar performant models. They also require training time modifications, limiting their general applicability. Verifiable computations require inference time alterations, such as changes to architectures or restrictions on what operations can be used. Prior approaches towards solving the aforementioned problems have several shortcomings. To create a verifiable proof for their efforts in training a model, Jian et al. Proposed a concept named proof of learning. With these verifiable proofs, arbitrators can use these proofs to resolve ownership conflicts. All central servers could use them to verify if delegated computation was performed correctly. Proof of learning, or POL, is defined as a tuple WIHA, where W is the sequence of model weights, I is a set of data indices used to learn the weights, and A is the auxiliary information that is necessary for training. Note that this is enough for producing and verifying a proof for a model that is trained on a publicly available dataset. If the training data is private, however, approval is required to provide signature of the data points. An adversary A might wish to prove a POL proof by spending less computation and storage than that made by prover T in generating the POL proof. By stochastic spoofing, adversary could produce a valid POL for FWT, but it is different from the one produced by prover, which means FWT prime equals FWT while T prime less than T. POL assumed that an adversary is capable of the following capabilities. First, it has full knowledge of the model architecture, model weights, loss function, and other hyperparameters. Second, A has full access to the training dataset D and can modify it. And A has no knowledge of prover's strategies about batching, parameter initialization, random generation, and so on. Note that the second assumption is essential in our attacks because our methods are based on the adversarial examples of the origin data. For the creation of a proof of learning proof, it is equivalent to recording the chain of the updates. However, to prevent the size of the proof from being prohibitively large, the prover can record the weights only every k steps, then P1, P2 until Pk-1 are removed, leaving only P0, Pk, P2k, and so on. This is done for every epoch of the training. The verification mechanism of the proof of learning is divided into two parts. First, for the initial state of the proof P0, to prevent adversary using a stolen model as initial state, the Cherenkov-Smirnov test is used to test if a set of values is sampled from a certain distribution. Second, stepwise verification is used to verify the rest part. In high level, the verifier verifies a proof by reproducing the training and say if they get the same final model. When training a model from the same initial state and use the same data for every k step, the verifier checks if the reproduced model is close to the corresponding model state in the proof. If so, The verifier loads the model state from the proof and try to reproduce the next k step based on this state, and so on. By estimating the entropy of the k step of time t, which called epsilon reproduction t, and set a delta that much less than dref, where dref is the entropy when retraining the model, it is easy to verify the proof. Now, let me start to discuss our attack intuition. Note that the verification is to reproduce part of the model with given start model and data. What if we could generate certain weights with well-designed data? If so, we can generate a sequence of intentional weights leading to WT, which could be much shorter than the original sequence. An adversarial example is an instance added with small and intentional perturbations, so that a machine learning model will make a false prediction on it. In a similar way as optimizing an adversarial example, we could make an arbitrarily chosen data point generate a given model. Take the step from W0 as an example. Like normal training process, we compute the loss and gradient dW0. Using gradient descent to get next weight W0 plus eta dW0, which denoted as W1 hat, and minimize the distance between this weight and the given weight W1. Similar to the generation of adversarial examples, we only optimize the perturbation and in the same time, we minimize the perturbation itself. By optimizing the perturbation to find the minimum of this objective function, W1 hat is getting closer to W1, and the perturbation is getting smaller. Finally, W1 hat equals to W1, and the perturbation is small enough to be indistinguishable. This progress of generating the perturbation is called adversarial optimization. However, each adversarial optimization needs a lot of computation, and the total computation is very large, even if we design a shorter sequence of weights. To accelerate adversarial optimization, instead of sampling models randomly, we sample the intermediate model weights such that the distance between Wt and Wt minus k less than delta and much less than epsilon reproduction t, where t mod k equals 0. Practically, A can initialize the weights after W0 by equally dividing the distance between W0 and Wt. If the number of steps for spoofing, for example T prime, is large enough, in other words, there are enough Wt's, the condition distance between Wt and Wt minus k less than delta can be trivially satisfied. Another major change in basic attack is that A optimizes the perturbation by minimize dW0 plus perturbation. These two changes make the adversarial optimization become easier to converge. Normally, it takes no more than 10 steps of adversarial optimization to get a convergent result. Notice that in basic attack, we have to generate adversarial examples for every step. An advanced attack is proposed to optimize all k batches of data points together. In basic attack, we need adversarial optimization for W0 to get W1, for W1 to get W2 until we get WK. In fact, we could optimize the k steps of adversarial optimization once, from W0 to WK directly. We formally prove that the extra error caused by advanced attack is acceptable. The details of the proof are discussed in the paper. Then we can compare the cost of the gradient calculations in the POL proof and in our attacks. In the POL proof, it needs t times of iteration. In basic attack, it needs t prime plus t primes times n times adver times of gradient calculations, where n equals 10, and adversarial optimization needs 3 times of gradient calculations. In advanced attack, it needs t prime divided by k plus t prime divided by k times n times adver times of gradient calculations. Same with basic attack, n equals 10 and adver equals 3. In practical, t is said to be 78,000 in POL proof. So we set t prime less than 2516 for basic attack, and t prime less than 251,600 for advanced attack, can provide a proof with less number of gradient calculations compared to the POL proof. Now let us see some evaluations. We conduct our attacks on CIFAR 10, CIFAR 100, and a subset of ImageNet dataset, and we show our evaluations on CIFAR 100 as examples. For basic attack, we can see that the time of attack and the time of POL proof generation crosses when t prime equals 1700. And the other two cross points are cosine norm and L1 norm epsilon at 1300 and 700 respectively. So setting t prime smaller than 1700 while larger than 1300 can be a valid attack. For advanced attack, t prime smaller than 4000 is effective false proof, and the other two cross points are cosine norm and L1 norm epsilon at 1300 and 700 respectively. So to generate a valid proof, we need to set t prime smaller than 4000 while larger than 1300. Recall that it is assumed that A has full access to the training dataset and can modify it. An implicit assumption is that V does not know the dataset beforehand. Otherwise, the attack can be easily defined by checking the integrity of the dataset. This assumption is realistic. Consider the scenario where two hospitals share data with each other, so that they can train models separately for online diagnosis. Suppose Hospital 1 trains a good model, and Hospital 2, which is the attacker, wants to claim the ownership of this model. Then Hospital 1 provides a POL proof, and Hospital 2 provides a POL proof. In this example, A knows the training dataset, but V does not. However, we could still check if one dataset is an adversarial perturbation of the other. This may introduce a new arms race. A would need to evade both POL and this second verifier. To this end, we evaluate the effectiveness of our attacks on two non-overlapping datasets. We split the dataset CIFAR 10 into two non-overlapping datasets. Then, prover and adversarial generate proof and sproof with these two different datasets. In this case, verifier can never know which dataset is an adversarial perturbation. Here we see the two cross points for basic attack is t prime equals 5000 for the time evaluation, and t prime equals 600 for the infinity norm. So we can prove POL when t prime smaller than 5000 and larger than 600. For advanced attack, the cross points of time evaluation increases to t prime equals 5900, and it remains t prime equals 600 for the infinity norm. So t prime can be smaller than 5900, while larger than 600 for advanced attack. There are still two countermeasures for our attack. The first is to design a more strict selection of threshold. As we observed in our experiments, epsilon reproduction in the early training stage is usually larger than that in the later stage, because the model converges in the later stage. On the other hand, epsilon reproduction remains in the same level in our proof. A more sophisticated way would be dynamically choosing the verification thresholds according to the stage of model training. Choose larger thresholds for the early stage and choose smaller thresholds for the later stage. However, we can also set the difference between WT and WT minus K closer in the later stage to circumvent this countermeasure. Another countermeasure is verifiable computation. We can use VC to build a secure POL mechanism. During training model, prover generates a VC proof, proving that the final model WT was resulted by running the training algorithm on the initial model W0 and the dataset D. However, it has to divert O(n) log n computation to generate a valid VC proof, which is almost equal as T. This mechanism is valid, but it will introduce an overwhelming overhead. Thank you for listening to our presentation.
Okay, thank you. Questions?
Hi, Nicolas Papelno from the University of Toronto. Thank you for the presentation. In the original POL paper, we described a variant where the data is hashed in the proof. Could you comment whether your attack is still applicable in that case?
In our works, we just neglect the hash for simplifying. In our works, we neglect the hash because we think that since the datasets are all unknown to the verifier, so we can build a hash simply. So that's the reason we neglect the techniques.
Okay, so I guess the reason I was asking is that in the paper we described a mechanism for the proof to contain a hash so that the verifier would be the only one given access to the data when needed on demand, and the adversary would not have access to the data itself. And I guess for context for people in the audience, I tried to reach out to you to reproduce the results, and we were not able to, so we wrote a blog post on cleverhunts.io where we explain why we cannot reproduce the results in your paper.
Okay.
Thank you.
I have shared our code on the GitHub, so you can reproduce our results with the code I shared online.
I'll be happy to try. The last time I wrote to you, you told me the code is messy and didn't respond. Okay, thank you.
Other questions? Okay, I'll ask one. You described the adversarial examples by making imperceptible perturbations to valid images. I'm curious if it would allow the adversary more ability to just make the images be completely arbitrarily noisy instead of having to be adversarial modifications of clean images. Is there a reason why you added this like sort of similarity distance as well?
Are you asking about the the picture's quality?
Yeah, so you require that the training data actually looks visually good.
Yes.
Other than the fact that a human might look at the training data set, would the proof check correctly even if the images didn't look high quality?
So the verifier will check the data. So since the verifier can get the data, so and check the intermediate models and their input. So we make the pictures very good looking. Otherwise, they will tell the difference from the generated pictures.
Okay, so you're worried about like manual inspection of the data?
Yes.
Okay. More questions? Sure, I'll ask one more then, which I know that you sort of have a comment on in the paper. I know the original proof of learning paper also talks about sort of randomness across GPUs and how sometimes it can be harder on some hardware but not on other hardware. If maybe you want to comment on that.
Yes, the different hardwares will have different capabilities. So especially for the advanced attack, it relies greatly on the hardware's capabilities. For the larger for the 32G capacity will carry more faster optimization for so in experiments
because limit of the capability of GPUs, we divided the advanced attacks. In fact, we divided the attacks in about 50, 25 different steps. So the GPUs are very important for our attacks.
Okay, let's thank the speaker one more time.